Okay, great. Yeah, so my name's Benjamin Zaitlin. I'm a software manager at NVIDIA, and I'm going to talk about GPU data science, which sounds like a crazy thing to do. But first, let's maybe take like a condensed historical look at what data processing has been like for the last like 10 or 15 years. So since the introduction of Hadoop, we had this workflow that was pulling off this distributed file system called HDFS. We query some data. We have to write temporary storage back to HDFS. We have to read back in. We do some ETL on those things. We write back to HDFS, and then we finally read all that data back out. And as we go down from the lines from Hadoop to Spark, we're getting rid of these gray blocks, the HDFS reads and writes. Like the major advancement, or one of the major advancements in Spark when it was first introduced is that it could do way more in-memory processing, whereas Hadoop could not. So we get a major improvement. We also got the community around data processing and analytics was thinking more about how to bring in a larger community into the space of data processing. So we go from Hadoop that's written entirely in Java. Of course, there are other tools like Hive SQL and other people that are trying to layer on top of these things. But we bring in more developers by reducing language complexity or inviting more people to the table. Still, though, there is an appetite to go, how do we get the next 10x after that? And people started experimenting with GPUs with Spark or GPUs with Hadoop. But in this world of data analytics where you would pull data off of HDFS, then you have to, unfortunately, move data from the CPU onto GPU memory, do some kind of GPU processing. And because GPUs are resource constrained, they don't have as much memory as traditional RAM, you have to write that data back out to the CPU. And you get back into that same cycle that you see at the very top where we're pulling from HDFS, then we do reads and writes back from GPU to CPU. And we need to get rid of those things to actually get significant speedups in our workflows. And Rapids seeks to do that. So we have this initial read that comes off of HDFS, and then we need to make the entire workflow exist on the GPU. So not just a fast CSV read or a fast HDFS read, not just a fast matrix multiply, but the entire pipeline has to exist on the GPU and reduce the amount of reading or spilling that we invariably have to incur when we write from GPU to CPU because of memory constraints. So Rapids and friends, cuPy is not developed by NVIDIA, but Rapids' approach to the PyData stack has been to accelerate individually and well accepted PyData tools on the GPU. So for NumPy, a group at Preferred Networks built cuPy. For Pandas, Rapids built cuDF, and for scikit-learn, we built cuML. So each one of these libraries is largely single GPU. There are some primitives to do multi-GPU things here, but we can, for this talk, let's think of these things as just a single GPU. So we can have accelerated pandas, accelerated machine learning models, or classifiers, and accelerated NumPy operations. And because we have those tools, we can then leverage other engines like Spark, or in this case, Dask, since we're at the PyHEP conference. I'll mostly be focused on Dask. So we can take those tools and accelerate the entire stack. So this is the Rapids kind of view of the world that we can take. We have cuDF, cuML, we can do graph analytics. Of course, we can interact with other deep learning frameworks like PyTorch, but we also care about visualization. Again, we really want to stay on the GPU in order to get that performance up. More recently, we've been expanding beyond just those kind of the building blocks of the PyData community. Specifically, we've added cuSIM, which is a SCIKIT image compliant API that is GPU accelerated, and cuSignal, which uses the SciPy Signal API. So really, we're just, for lack of a better term, like thieves within PyData. We take these APIs that become like NumPy and Pandas becomes the API definition, and then we use that to build our own libraries. And the contract here is that with minimal code change and in API compliance, you should get not just 2 or 2.5x, but 40x or 50x performance gains across an entire workflow. So far, we've been pretty successful. This started off kind of as a grand experiment. We had to reject a lot of assumptions that we had. But over time, we've seen kind of explosive growth. We started in late 2018. And in 2021, we're getting very nice downloads or usage of Rapids. I should also mention that unlike in the past, where getting to the GPU, or at least in my experience, getting to the GPU is really hard, not just computationally, but also individually. Writing CUDA kernels is extremely challenging. Getting domain experts to learn CUDA to accelerate any of their workflows, be it in biology or in high energy physics, is a hard ask. NVIDIA has now decided to invest the resources to build out these libraries ourselves, invite other contributors from the community to help, but there should no longer be that pain of getting to the GPU because you don't know CUDA. That we're trying to leverage the community and spend the resources ourselves in order to build these libraries. So in this talk, while Rapids has a very expansive portfolio of libraries, we're mostly going to be focused on Dask, cuDF, and cuML. So within Rapids, many of the libraries have the following stack, where we have an underlying layer of C++ and CUDA. We leverage common GPU or CUDA libraries like Thrust and Cub. We then add a Python layer to give us Python hooks. So there is a well-established libcuDF C++ library that some users actually will use directly. People that, in my experience, mostly those users are in HPC, though there are some business cases where C++ is the desired language to use. However, we think that in order to get wide adoption of GPU usage for data analytics, we needed to provide a Python interface. Though there's nothing that really prevents us from adding other languages other than resourcing and interest. So again, cuDF provides a familiar pandas-like API. We don't cover the entire API because pandas is extremely large. We've also made some judicious choices where some of the defaults in pandas will inhibit performance. So things like group by aggregations will, I believe in pandas, like they come back sorted, and on a GPU, these aggregations are non-deterministic. So sorting actually prevents us from getting more performance. So we make some small changes here, but it should be extremely familiar to anybody who knows pandas. Again, some obligatory benchmarks. What we see when we compare pandas to a single GPU, so this is a V100, which is actually a slightly older GPU, to a fairly high-powered CPU, we get sort of off the charts performance benchmarks. I want to keep reminding folks that it's not about, we're not trying to create the fastest merge or the fastest sort, although in aggregate, we're trying to create a significantly faster workflow. So while we have merges that are 500 times faster, or faster sorts or faster group bys, what you should be asking yourself is, how fast is the end-to-end workflow? Because if your problem is do all of your work on the CPU and then just do a very fast sort, that might work for some business cases, but it doesn't work for the far majority of users who aren't bound by a single group by, but that are bound by the pipeline, which involves I/O, specific querying, a lot of ETL and ML, and some viz. I really like this slide because this is where I get to talk about how rejecting assumptions. We tend to think of GPUs as being just good at dense linear algebra, neural networks, drawing lots of triangles. Those are what we think of as what GPUs are used for. And when Rapids first started, it started off as kind of research, as an experiment. And that meant rejecting some assumptions that we had about GPUs, which going into this, most people will say GPUs are terrible at strings. And it turns out that they're not actually terrible at strings. It's not the wheelhouse of what GPUs are good at, but it turns out that they're quite performant. And there's things that we can even do to push on GPUs to make them even better. Because strings actually show up everywhere, we needed to confirm this, and we needed to actually push on things, push on string performance being as fast as possible. It is rare the case that when you get into analytics that you will just have numerical data. ETL kind of is always present, whether you're doing business use cases or image processing or even high energy. Strings kind of find their way into any workflow. On the ML side, we see something that looks a lot like cuDF. So cuML is, again, a library that maps to the SCIKIT Learn API. The structure of it, again, is underlying CUDA libraries where we can call out to cuRAND, cuBLAS, cuSolver. All these libraries have existed for a long time. It's just not wrapped up in a nice package for PyData users to go out and consume. From those things, we can now build out cuML algorithms, linear regression, random forest, and we can add Cython to give us Python hooks. So we can use in the Python ecosystem. Just like with cuDF, we get very good performance, although varied performance depending on the algorithm. Not every algorithm will scale as efficiently on 1,000 threads that GPUs have to offer, but we still get very, very good performance across a wide variety of algorithms. So right now, I believe we have 26, at least the slide tells me 26 GPU algorithms or GPU accelerated algorithms, but we're always looking to increase this. So if you have, we're very responsive to community feedback. If you have algorithms that are not supported that you need for your workflow, please come to our Slack channel, which I'll post at the end, or even on GitHub. All of this work, again, is open source. We work in the open, trying to engage the community as much as possible. The nice thing also about cuML is that it's trying to GPU accelerate the classifiers. So we can still leverage the other machinery inside of scikit-learn. We're not trying to build a hyperparameter optimization engine, but scikit-learn already has that. And because our objects speak and look and feel like scikit-learn objects, or the classifiers at least, we can leverage the rest of the machinery within that library. So as I said before, we can generally think of these tools as single GPU. So we need other tools to scale out that performance. So on the left, we have how we can scale up and accelerate things. And as we move to the right is how we can scale out and parallelize things. So Rapids can leverage tools like Dask or Spark or Blazing SQL, which provides a SQL engine on top of Rapids. And we can also leverage, although it's not listed in the slide, accelerated networking devices like NVLink or UCX. Those devices, UCX can use, there's a lot of, let me back up because there's a lot of kind of meat in that. When you scale out, very quickly, the bottleneck of your problem becomes networking. As such, people want to accelerate networking just like they want to accelerate computing. For GPUs on a single node, you can pass data back and forth with something called NVLink. Between nodes, many accelerators or many people turn to a device that's built by Mellanox called, or a networking protocol called InfiniBand. which lets you do RDMA or GPU RDMA, and generally has higher throughput compared to regular Ethernet. Dask and Spark can leverage those kinds of accelerated networking devices. So what is Dask? Dask is a Python library for parallel computing. Dask comes from the idea that we have this very large PyData stack, and many people were at the time this was built 6 or 7 years ago, I think. We had this very well-known stack that I've said actually many times now already: NumPy, Pandas, scikit-learn. How do I make this go even faster? I have this on my desktop. I have a laptop, and underneath I have a desktop. Both have multiple cores. How do I make multi-core, multi-threaded NumPy or Pandas or scikit-learn or the next PyData library? There have been a number of attempts, and there still are. Hopefully many will succeed. Dask takes the approach that rather than trying to build a distributed NumPy from scratch, we'll figure out how to just use NumPy blocks or Pandas blocks or scikit-learn blocks as the unit of data that I'm working on. So we have a distributed Dask array that is just comprised of NumPy objects. So all of this should look very familiar to you if you have ever used NumPy or Pandas or scikit-learn. Similarly with Pandas, Dask takes the approach that I'll just have many Pandas operations, and I'll write algorithms that can operate on, many Pandas blocks, and I'll write algorithms that can operate on many blocks at once. Because RAPIDS implements, or because cuDF implements a Pandas-like API, Dask can use cuDF. Because CuPy has a NumPy API, we didn't have to change a dramatic amount inside of Dask to leverage CuPy objects inside of NumPy. To be clear, there was work that needed to be done, but most of that work was around generalizing what arrays are. And those things happen in the NumPy community. They've also happened inside of the Dask codebase as well. Similarly for Pandas and for scikit-learn. So again, I can take NumPy, Pandas, and scikit-learn. And on the next slide, really just a quick change, I can now have a distributed version of Pandas and NumPy and scikit-learn, or CuPy, cuDF, and cuML. So Dask, briefly, is more than just big Pandas and just big NumPy or distributed NumPy. There's a lot of code a lot of very complex code in already existing code bases that look like this. This one happens to be Pandas, where we have some function that takes in some data in a model and it spits out some other data frame. You might write a for loop over many results, over a number of lists, and run these two functions and collect those inside of a larger list, some result. A nice bit of syntactic sugar around Dask is to let us create a task graph, create a graph on the fly. So we can annotate these functions with Dask delayed, and they become delayed functions. So Dask will lazily traverse all of these, this graph that you construct on the fly, and then the Dask scheduler will find where work can be done. So we've already added parallelism to an existing code base with just a little bit of work. Because I can do that, I can now take each one of these tasks can be executed on a node somewhere in your cluster. Let me see, there we go. So your cluster is made up of parallel hardware. It either is a core, it's a multi-core CPU, it's a cluster with an even larger CPU, or a cluster with CPUs and GPUs. In the future, this could be clusters that have any kind of other hardware, and Dask should be able to fit comfortably within there as long as it can speak to that, as long as there is a Python library that can speak to that underlying hardware. We spent a lot of time within the Dask community thinking about how to deploy. Many of these are open source projects, though now there are full-fledged enterprise companies built entirely around Dask, like Coiled or Saturn Cloud. Previous to those companies, we spent a lot of time thinking about how to leverage cloud native tools like Kubernetes or ECS. There's things for Azure ML and things on Google as well. We've also spent a lot of time interacting with the HPC community and handling the variety and strangeness of batch schedulers like PBS and LSF and Slurm. I think there's even some drama deployment tools as well. Or now older scheduler or hardware schedulers like Yarn. We also have a good support for running Dask on those clusters as well. Sorry, I'm getting a little short on time, so I might skip ahead. So it was done purposefully that Rapids tried to kind of attack not attack, but leverage or engage the PyData community, and then use tools like Dask to scale those things out. Because we are, or Python users need a lot of feedback. We also continued pushing on getting feedback of what's happening. So many of us actually that came from the Dask community to help with the Rapids effort. We're not GPU experts, but we knew a lot about all these other tools. Dask has a very sophisticated dashboarding system, as you can see in this previous slide that I can't get back to. Here. So Dask has a lot of dashboarding tooling to tell you about what's happening in the task stream, about what's happening per task, of whether I'm doing a particular read or merge, and give feedback to help users understand where their workflow is performant and where it's slow. But as I said before, many of us didn't actually have deep GPU experience, and we needed more tooling to tell us what's actually happening on the GPU. We wanted a nice warm fuzzy feeling that when I did a GPU thing happened. And before, like there's tools like PyNVML that could tell you, or NVML that would tell you what's happening on the GPU. And it wasn't too difficult to just write a little bit more Python code, connect it up to dashboarding or to visualization tools like Bokeh, and integrate with JupyterLab. So now we can get real-time feedback about what's happening on the GPU, whether it's the utilization, the memory consumption, PCI throughput, really anything that NVML has to offer, we can visualize. We can tell you about the power consumption, tell you anything that the GPU actually tells its users. We can go query it and visualize it. And that's really great. It's so wonderful that all these tools actually can come together very easily for us to iterate quickly and build out these dashboards. Sorry, so when I said before, what we're trying to sell you on is not, or pitch is not just a fast merge or fast sort or particularly fast ML algorithm. It's really this end-to-end workflow. And this slide tries to break that down. This is for a mortgage data set, XGBoost training model where you're trying to predict house sales or rental prices, I think. I think it's the Fannie Mae and Freddie Mac, which is a standard data set for ML training. So we break this down into what it looks like for just reading in data. So just pulling data off the disk. This happens to be 200 gigabytes of CSV. What the XGBoost learning looks like, that the ML algorithm that you're applying to this data, and then stacking this all together. So it's not just a fast read CSV, and it's not just an XGBoost that's really fast. It's really the end-to-end that's significantly faster. And what we see is that with, in this case, the A100s are the new NVIDIA GPUs, but we even saw the same performance or similar performance with V100s, that we can get significantly faster performance and cheaper. So it's really like the most perfect kind of pitch. Like, here's this widget that's faster and it's cheaper than the competitor. But that's what we're going after. Within NVIDIA, within Rapids, we're very cognizant of the fact that GPUs are non-zero costs, that they can be expensive. So we are always trying to push for getting not just higher performance at a higher cost, but higher performance at a significantly lower cost than building out a similar pipeline with CPUs. Sorry, I'll go through these quickly. There's also a very sophisticated graph analytics Python GPU library that maps to NetworkX. This is the current list of supported algorithms. We're continuing to expand. More recently, we've been going after minimum spanning trees and continuing to push fast for more and more on getting better performance in PageRank. For visualization, we've also worked with Plotly and within PyViz to interoperate nicely with HoloViews and Bokeh, because we can pass data back and forth with cuDF. And then more recently, there's been a very exciting development where people have built node hooks directly into Rapids. So no Python, just JavaScript and GPUs. So we can build really sophisticated visualizations that are just JavaScript or just NodeJS. As I said before, the Rapids is rather expansive. These next two slides kind of show what we're trying to go after, where we think the maturity is, and the performance level, and who's currently using these things. So cuDF, cuML, we already covered. Briefly, cuGraph, Rapids Viz. We're continuing to expand on other domain-specific libraries like cyber log parsing or analytics, image processing, signal processing, spatial processing, streams, recommender systems. We've done a ton of work this year. We have even more. We're trying to push even harder on more improvements with cuDF. Those are both more improvements that are performance-based and also usability, going after things like better time series support. We have a wide variety of partners and adopters that expand both the contributors across the ecosystem, across the open source ecosystem, and adopters within business. We've also had a lot of uptake of Dask and Rapids within research and academia. So folks at Slack, MedOffice, Atlas at LHC. Unsurprisingly, Rapids has a lot of usage within NERSC and at Oak Ridge, where they built very large GPU clusters. At the bottom, I've included some links to Dask held a summit recently. And folks here like Jim Pravarsky presented at Dask in HPC and Dask in high energy physics. We can deploy on all these clouds. You can also engage enterprises like Coiled and Saturn Cloud for help. Please come join us. Here's a bunch of links to help get started. Thanks. I'm sorry I ran a little over. So I might not have time for questions.
No, you're good. Thanks very much. If you can stick around we're at the break, but if you can stick around for maybe 1 or 2 minutes, we can go to Slido. I think you have the link, and we can try and answer a few questions there.
Sure. Yeah, so one person asks, ML frameworks usually have dedicated solutions for distributed multi-GPU, multi-node ML. Do you see this moving to Dask? Yeah, we see a lot of people that can do partial fits actually can leverage Dask ML very nicely. Within the cuML group, they want to use, they often will write their own distributed GPU, own distributed ML solution, because they can be more performant than Dask, but they will still use Dask to help set up all of the networking and be able to, they actually have very challenging problems where they want to leverage networking tools like Nickel to do like all reduces that Dask currently can't do. But many people are still moving to Dask to write distributed algorithms, or at least write things that can work alongside Dask very, very nicely. Another person asks, how do these efforts compare with other GPU-oriented libraries such as TensorFlow, PyTorch? How are they meant to work together? Yeah, so the community, the PyData community has pushed on things like the CUDA array interface. So I can move data between different libraries with 0 copy efforts. So as long as your library speaks the CUDA array interface, I can move data between cuDF and CuPy and PyTorch. There's other things that you want to consider as well, like external memory managers. So PyTorch, unlike in the CPU world where NumPy kind of became the de facto memory manager as well as the compute engine, in the GPU world, everybody wrote their own memory management systems. However, people are now adopting tools and techniques to allow for external allocators. So within cuDF or within RAPIDS, there's a tool called RMM, the Resource Memory Manager. And we're asking or trying to help other tools like PyTorch, I'll come to TensorFlow in a second, leverage external memory allocators. So CuPy can use an external memory allocator. So we can not only pass data 0 copy, but we can also use one memory allocator across all of the libraries. We've not had as much luck with TensorFlow. They're not as, at least in my experience, as engaged as the PyTorch community is with trying to adopt standards that the community is trying to put forward. But other tools like JAX kind of have started to adopt some of these things. Yeah, another person very correctly points out that on the slide comparing strings, on this slide, that Pandas uses Python objects for strings, and they want to know how this compares with precompiled string handling. The answer is I don't know offhand, but I wouldn't be surprised if GPUs I would still expect GPUs to be faster, though I don't know how much faster. Precompiled string handling would be a significant gain for Pandas or for Python if that was ever adopted. But that's a more than valid point. And in many of the comparisons, we try to be as open about what's actually being compared. There's an old slide comparing cuGraph to NetworkX, for example, and that shows like bonkers performance, like 1,000 or 2,000x faster. And that's because NetworkX is Python only. There's others networking tools that in production use cases would probably use, even though they might start off with NetworkX because it's easy to use, but you'd go to something else for performance. But being open about that is something that is highly encouraged within the group. Another person asks, how easy is the hardware to acquire / roll out? My usual issue is access to GPUs, to a GPU or multiple GPUs in the first place, even before thinking about using them efficiently. Yeah, so there is a tool. Right now we're pointing people towards Google Colab, which is here. If I click this link, this will bring me to a hosted notebook on Colab. This is just to get started. Many people are trying to, by many people, I mean folks like Coiled or Saturn Cloud. There's another company called, I think it's called Paperspace, that are trying to make, or at least demoware of, or one-click GPU accessibility a thing. So now that I have this notebook on Google Colab, I can change the session. No, that's not it. I can change my runtime type to GPU here, or I can actually ask for a TPU. The kernel will restart and it'll run anyway. Let's see. This time I got a Tesla K80. So I can, depending, and Google supports T4s, P4s, or P100s. Still though, we've been thinking, RAPIDS has been thinking about, and other companies as well, about how to make GPUs just more accessible in the first place. I think this page, rapids.ia/cloud, shows an overview of what is currently supported, how to get easy access to things like SageMaker or a single instance using with Dask. In the past few months, I've had trouble getting A100s on Google and EC2. I believe they've been purchasing more, so it's getting easier, but there's still some challenges there. We've tried in the Dask community to make this as streamlined as possible. So tools like Cloud Provider, where we can go ask to get a GPU on Amazon, can be done kind of seamlessly. I think there's maybe an example here. Somewhere in these docs, there's examples of getting to Rapids, but getting time, when I've done some testing on Summit, on ORNL, it's not been hard to get time to, so many clusters actually have very large GPU hardware locally.